Yeah, we'll talk about the self-bias circuit. Homework number 2. Basic circuit is this. PMOS current mirror and the NMOS current mirror. But NMOS current mirror has a resistor in the opposite side of a diode. Okay? Then, when the transistor works in a strong inversion, then current should be around 2 mu Cox W over L. This W over L is actually this W over L. Okay, R square. That's for strong inversion. But in a subthreshold, the equation looks different. Yeah. So here, see, let's in a subthreshold, the current equation is just this one. What is that? Mu Cox W over L 2 square root 2 pi f minus VBS of thermal voltage square exponential gate source voltage. Something like that, right? This is your subthreshold current equation. So we'll just use this part of the equation. Or say, for this loop, we have a different W of L, right? The other parameters are the same. So let's just see. I assume the same threshold voltage, okay? So this is M1, this is M2. Then KVL says VGS1 plus IR should be VGS2, okay? Then how can I calculate this voltage, this current I? Yeah, I1, which is current of M1, is some constant times W of L is 4, then exponential VGS1 minus VTH of NVT. Current of M2, 4 times 1 exponential VGS minus VTH at 2. NVT, right? Then, actually, this current is the same, right? Those two currents are the same. Then, see, I can find so let's just see. Say I just divide it. Then what's the exponential? So it says 4 exponential. I divide the equation 1 by equation 2. VGS1 minus VGS2 of NVT should be the same, right? Okay. Then this is only this part. This is only I times R, right? So my I is only 1 over R. What is that? Log 4. MVT log 4. So this is my current in a subthreshold equation, okay? So let's just see. Yeah, so it has this is a W of L ratio. So the current should be inversely proportional to resistance value, almost, right? Any question?
그 정페이지에서 저기 처음에 이제 저 회로에서 이 R 값이나 이런 거는 이제 커런트 값을 만약 설정하면 이렇게 R 값을 정하는데 처음에 이제 식에서 만약에 VGS랑 모르는 게 만약에 W 값을 모르실 때 그러면 식 거기서는 W 그 VGS1 마이너스 VTH가 얼마라고 가정해서 W 해보고 그 다음에 이렇게 W 값을 대략 정하고 VGS 값을 바꿔야 되는 그런
Yeah, question is how to determine W of L, right? Yeah, but actually W of L does not show up in the equation. The requirement for W of L is the transistor must work in a sub-threshold operation, right? Not in strong inversion. If you have, say, for example, say I have some target current, right? Then my WL should be very large for transistor to work in a sub-threshold operation, right? You have a target current. It must work. The transistor must work in a sub-threshold region. So my WL should be larger than some value, right? Yeah. Maybe you can use sub-threshold test. Say sub-threshold test is very simple. Say sub-threshold test. Then you just sub-threshold test is just something like that. For the NMOS, for the PMOS. So this is my sub-threshold test. I apply some voltage and then find the current and then plot logarithmically. This log I V. So if for certain WL, this is my target current, right? I target. If it works in this linear region, it works in the subthreshold. If I reduce my W of L, say it will be something like that, right? So it works in a strong inversion, right? So my W of L should be large enough for subthreshold operation. Okay? Yeah, you can test it by SPICE simulation. Okay, so here's that self-biased circuit. Self-biased. This self-biased current source is insensitive to VDD variation, supply voltage noise, supply noise, right? Current is insensitive to VDD, right? That's a very strong point of this one. Yeah, it has some temperature dependence. Okay. Yeah, the other point is this self-biased circuit is a positive feedback circuit. Yeah, so you can see if this voltage is increasing gate voltage, this is a common source amplifier, this should be negative, right? That's a property of a common source amplifier, this PMOS. And this is a negative, then this common source transistor, this is positive. Ooh, so this should be a positive feedback, right? Yeah, common source amplifier, voltage gain is negative. Okay. You know, common gate, the voltage gain is positive. Common drain, voltage gain is still positive, and slightly smaller than 1. So we have to find the loop gain. If loop gain is larger than 1, the circuit oscillates. Okay. Now, how can I find the loop gain? Let's see. Yeah. Yeah, loop gain of this self-bias circuit, yeah, can be, say, I just cut the loop here. See, I will cut the loop here for this MOS side and then apply some current, test current here. This is small signal current. And then here I have some resistance here, and then PMOS transistor there. This should be PMOS diode, right? Diode. And then I have another current PMOS transistor there. And then I just calculate this I out. So my loop gain is just I out divided by I in. Okay, this is I in. Okay. Yeah, for this one, see, yeah, this is I2, right? This is I2. Actually, this is because this is 1-to-1. My I out should be just I2. Okay. Then what's I2? Yeah, say you can find the small signal equivalent circuit. See, this is M2, right? I said this is M1, this is M2, okay? Yeah, to find the I2 from I in, I will use small signal equivalent circuit. So, yeah, that one is, this is, yeah, this diode, the M2 diode is actually this GM2, one of GM2, and then, yeah, what else? Yeah, one of RO2, something like that. So I have I in there. This is my I in, okay? And then this is connected to there. And then for this T equivalent circuit, one of GM1 here, and then one of R2 there, and then, oh, this is connected together. And then what else? Yeah, this is I2, right? If this is I2, that is I2. I2 0. Say, and then I have some RO2 here. Oh, this is RO1 actually. Oh, yeah. So this is my I2. This is my I2. So I neglect those RO stop because my RO is much larger than 1 over GM. Okay? Then it's easy. I neglected GMB already. GMB is neglected. Set to 0. I neglected GMB1. Yeah, then let's see what's I2 0. This is I2 0, right? I2 0. I2 0 is say, you know, the voltage. I know current is 0 here because gate current is 0. Okay, so this voltage VG1. This is VG1. Actually, VG2. VG2. VG2 is only this I in times 1 over GM2. Then I can calculate easily I2 0, right? This actually I1 0, sorry. This is I1 0 because this is M1. So what's my I1 0? I1 0 equal VG2 divided by 1 over GM1, 1 over GM1 plus R2. Okay. So I just substitute VG2 in this equation, then I can find this I1 0, which is I2, right? So my I1 0 is VG2 divided by 1 over GM1 plus R. So this is I in times 1 over GM2, right? 1 over GM1 plus R. So, yeah, actually I2 is the same as I1 0. because I neglected RO. Yeah, because RO1 is much larger than those things. Actually, not this one. My previous equivalent circle has something wrong here. Oh yeah, sure. This should be there, right? Not there. This RO1 must be connected between drain and source, right? Okay. So my I2 is I10. So my loop gain, which is I2 over I in, is 1 over GM2 divided by 1 over GM1 plus R, which is larger than 1. So no oscillation. Okay? Although it is a positive feedback, it doesn't oscillate. Okay? It works in a stable way. In a strong inversion, it is just 1/2. Loop gain is just 1/2. You can find it. All right. How about the sub-threshold? Sub-threshold. What's the loop gain? Loop gain is, I think it is also 1/2. That GM thing. GM in sub-threshold is just ID over MVT, right? If they have a same ID, then they have a same GM, okay? You know, in two branches, the same current flows, okay? Oh, is it 1/2? Oh, let's just see. How about this R? This R is, I know this R is, let me check. IR drop equal MVT, right? Is it right? MVT log 4. That's my IR drop, right? And then see, what's R? R equal MVT log 4, oops, where am I? Log 4 divided by I. What's the GM? GM equal I over MVT. Oh yeah, there should be log 4 there, right? So in the loop gain is not 1/2. This loop gain is log 4 plus 1 or something like that. Okay, it should be slightly smaller than 1/2, right? Question.